Optimization is a concept derived from solving problems using mathematical models and derivatives in calculus. Optimization problems can involve polynomial, simple rational, and exponential functions drawn from a variety of applications. In this video, I will show you all how to solve optimization problems involving polynomial functions. I will put an emphasis on situations we encounter in our daily lives. A manufacturer needs to mix a cylindrical can that will hold 1.5 liters of liquid. Determine the dimensions of the can that will minimize the amount of material used in its construction. The first thing we should do is we should illustrate out the situation with a diagram so we can get a clearer picture of what's going on. And the next step is to create a corresponding mathematical model. So we are given that the volume is equal to 1.5 liters, which is 1,500 cubic centimeters. The volume of a cylinder is determined by pi r square h, where r is the radius of the base of the cylinder and h is the height of the cylinder. And we can say that pi r square h in this situation is equal to 1,500 cubic centimeters. Now that we have two equations, the area and the volume of the cylinder, what we're trying to find is r, the radius of the cylinder, the base of the cylinder, and we can do that easily by substituting the volume formula into the area formula, but we can't do that directly because there is no pi r square h in the area formula. What we can do is we can find h using the volume formula, and we can substitute h into the area formula, and thus we only have one variable in the formula for the area of the cylinder. Remember, pi is not a variable, pi is a fixed value. We are now able to express a as a function of just one variable, which is r. So therefore, we are able to solve for r. h equals to 1,500 over pi r squared. Therefore, a equals to 2 pi r squared plus 2 pi r multiplied by 1,500 over pi r squared, which is equal to 2 pi r squared plus 3,000 over r. To find the absolute minimum value of a equals to 2 pi r squared plus 3,000 over r, we can use the first derivative test for absolute extreme values. The derivative of ar is equal to 4 pi r minus 3,000 over r squared. And the said function 4 pi r minus 3,000 over r squared can be further simplified into 4 pi r cubed minus 3,000 over r squared. And since that r is more than 0, the only critical number is r equals to the cube root of 3,000 over 4 pi, which can be further simplified into the cube root of 750 over pi by dividing everything by 4 within the cube root. And a prime r, which is the function for the minimum area to be used to manufacture the cylinder, has to be more than 0. So we can just substitute the value of r equals to the cube root of 750 over pi into that function a prime r, and the resulting value that we get would be 725.39 centimeters squared. Oops, I forgot to write the a prime r. And finally, therefore, we can determine the height of the can, which is h equals to 1,500 over pi r squared, which and we know the value of r. The minimum value of the area of r is 750 over the cube root of 750 over pi. So therefore, we can substitute that into the equation, and we can obtain the final value of 12.40 centimeters. for the height of the can. And that was a good example of when optimization is used, and optimization can be used in fields from manufacturing to planning, to minimize costs, to maximize area, and so on. And that's all for today, and thank you for watching Rain Lee Calculus videos.